Hello everyone, how are you all doing? Welcome to IGBits. We train, you learn. Today we shall continue our topic work per energy. We will see some more sums. Alright, without further delay, let's get started. We have our YouTube channel. Visit us at IGBits in YouTube. Please feel free to subscribe and click on bell icon to get the notifications. Your support is very important for us to work together to share many more knowledge sessions across. Okay. Thank you all who are actually being with us and supporting us. This is a great platform that we are aiming for. Thank you all once again. Let's look at energy. Energy is defined as a capacity or ability of a body to do work. Capacity to do a work is called energy. Energy is also scalar quantity. Okay. Energy and then work. The units and dimensions are same for both. And then SI units for the work is joules. So energy is also joules. Okay. So we studied a different energies, right? Kinetic energy, potential energy, electrostatic energy, magnetic energy, geothermal energy, elastic, and then solar, right? So 1 erg equal to 10 to the power of minus 7 joules. 1 calorie equal to 4.2 joules. 1 kilocalorie equal to 4.2 joules into 1 kilowatt hour, which is nothing but 3.6 into 10 to the power of 6 joules. 1 electron volt equal to 1.6 into 10 to the power minus 19 joules. So these values we may end up using in solving the problems. But most of the cases, the problem when we attempt to solve the problem, I think they were given what value you're supposed to use it. If not, you have to just apply the standard, the values. Okay. So energy, I'm repeating, energy and work more or like same, but except that like an energy means, the capacity to do work is called an energy, but the calculation, the value, units, dimensions, everything remains same. Sometimes like you can think of like the dimension formula like for energy and work same or not, right? The following physical quantities having same quantity, I mean same physical dimension and then units. In that case, you have to think of like a work and energy would have same units and dimensions. Clear? Let's move on the next topic. So let's look at a work energy theorem. This is simple thing. We know that, right? V square minus U square is equal to S. In the kinetics, we studied this. V square minus U square equal to S, where we have not considered the mass, a point mass. Let's say we have a mass, then let's apply the mass for the both cases. What happened? mv square minus mu square equal to 2 mas is what is written. Let's divide it by 2, both left hand side and right hand side. So f mu square minus f mu square equal to 2 by 2 is cut fit and then mas is left over. So half mv square means a kinetic energy. We know that, right? Kinetic energy is nothing but k equal to half mv square, mass into velocity square, right? When you calculate the kinetic energy, we always remember that we are using a reference point, the frame of reference. So calculation of kinetic energy is always depends upon frame of reference. Let's assume you are traveling on a train. So train is moving, but you are not moving, right? With reference to frame of reference as a train, you are not moving. In that case, your kinetic energy would be the zero because your velocity is zero. But with respect to ground, maybe you are moving because you are moving the velocity at which the train is moving. So right, that's why these calculations always depends upon frame of reference. Okay, so let's say k is directly proportional to m, k is directly proportional to v square. Sometimes like you will end up actually getting a small formulas. Okay, let's come back to here. We know the momentum. Momentum is nothing but m into v, right? Mass into velocity. Rewrite this function now of m v square. Let's multiply and divided by m. So what happens is like f m into m square divided by m into v square, right? So now mv square, m square v square by 2m. mv means like momentum. So I can rewrite m square e square in terms of p is like p square by 2m, right? So p square equal to 2km, p equal to root over 2km or 2mk, right? K is a kinetic energy, m is a mass. If you have a kinetic energy and then mass, then it would be easy for you to calculate the momentum, right? That is why I'm written. Sometimes they will ask you to actually find out if the masses are actually doubled, what happened to kinetic energy? When velocities are doubled, what happened to kinetic energy? Those kind of scenarios where we can actually apply this formula. Okay, comes back to here half mu square half mu square. V means like final velocity, u means initial velocity. So the kinetic energy of at final, kinetic energy at initial, the delta of ke would be your work done, because ma means force into displacement, right? Force into displacement nothing but your work. So the work energy theory clearly stating that change in kinetic energy is nothing but your work done, right? Are you clear? So we use like v square minus v square, we use like half mu square, and we also talks about it, delta of kinetic energy equal to work done. We also talk about k is equal to half mu square, how it is uh, depends upon frame of reference. We also talk about like k is directly proportional to m and v square, and then we are expressed momentum in terms of like a kinetic energy using this, right? So these are the formulas which we will be using in solving the most of the sums. Let's see this one. A body of mass 0.5 kg travels in a straight line with a velocity is given, variable velocity, where acceleration is also given. Find the work done by net force during its displacement from x equal 0 to x equal 2. That is what's given, right? So what is given? M is given 0.5 kg, and then velocity v is given, velocity v a x 3 by 2. Let's say at x equal to 0, right? So what would be the velocity? That's a v1, v initial, a into 0 power 3 by 2, which is nothing but 0 meters per second. At x equal to 2 meters, the final velocity would be a into 2 power 3 by 2, right? This is what is given. Okay, and if you look at a is also given 5. Okay, so 5 into 2 power 3 by 2 is what is given, right? So work, how do you get a work done? In this case, when you look at velocities and mass, obviously work done is nothing but increase in kinetic energy, change in kinetic energy. So delta Ke would be your work done. So F m v final square minus F m v initial square. The vi0, this is gone. So what is left over is final. F into m is 0.5 into 5 into 2 power 3 by 2 whole square. This is what's the left over, right? So F 0.5 into 5 square into 2 power 3. 2 power 3 is nothing but 8. So let's make 0.5. So 120, how much this one? 25 into 8. 2 ones are 2 fours are. 425 is 100. 100 into 5, it's nothing but 50. Isn't so? So 50 joules would be our answer. Let's see this problem statement. A person of mass 70 kg jumps from stationary helicopter from parachute open. As he falls through 50 meters height, he gains speed of 20 meters per second. Find the work done by viscous of air trap. So what it reminds me, we have to understand the work energy theorem application. As so, if you look at the work energy theorem, what it talks about, work energy theorem, what it talks about, net force, net work done by all forces. You would say that net work done by all forces is equal to change in kinetic energy, right? So change in K is what it tells. When you say net work done means work done by the gravity, right? Work done by G plus work done by air drag is nothing but change in kinetic energy, V square minus U square. That is what you have to solve the problem. This is what they ask. Work done by G, we know mgh, right? Mgh. What is the value? M 70, G 10, and H 50 meters. Plus, let's say this is called X. X equal to F. What is M value? 70. Okay, V square. So 20 square minus 0 square initially at the rest. So how much X value now? This 2 and 0, 2, how much this is? 35,000 plus X equal to 14,000. Correct? So X equal 14,000 minus 3500. It implies minus 21,000. So 21,000 joules because this is work done. That would be your answer. Very clear? So work energy theorem is nothing but net work done by all the forces is equal to change in kinetic energy. If you know this line, then you should be able to solve this problem easily. Good example. Okay, try to actually see some more work energy theorem problems. Then you should be able to understand the given problem and then see like when we have to apply work energy theorem and then to solve the the given ask. What is meant by potential energy? Let's say you have the block of mass m, right, which is on the ground. You are started lifting to certain height, let's say h height. So what this means is the energy possessed by a body by virtue of its position or configuration or state is called as a potential energy. So we know that like what sort of force is actually applying on the body is like a gravitational force pulling downwards. F equal to mg because g is in downward direction. Agree? So let me put this in a highlighter form. This direction we have mg. Correct? The downward direction I meant to say. Okay, sorry guys. So what I wanted to show you here, perpendicularly downward direction, is called mg, which is nothing but fg, right? So downward direction. So F equal to mg, a gravitational force. H is called height that you lifted. And then now we are talking the work done. Work done equal to F into S, F dot S. So gravitational force into height lifted. So which is nothing but mg into H equal to mgh. Okay, this is like a simple multiplier. Let's not assume this is a cross product. Okay, this is basically a dot product. So work done is stored as a potential energy. In this case, your work done is nothing but your energy stored in this context. And then energy is a scalar quantity, so potential energy would also be a scalar quantity. The work, energy, power are the scalar quantities. Make a point. Let's look at this problem statement. A ball is released from top of a tower. Then calculate the ratio of the work done by force of gravity in first, second, third seconds. Right? That's what I ask. So what we see is like let's say we have a tower and then we are dropping the ball, release the ball. So in first second some distance, second second some distance, third second some distance, let's say, right? So H1, H2 and H3. So work done means what in this case? Potential energy, mgh. So work is directly proportional to H only. M is constant, G is constant, H is a variability. So how do you calculate H? If you look at a kinetic theory, in the what we studied in the kinematics, Snth formula, Snth equal to U plus A by 2 into 2n minus 1, right? So that means like Snth is directly proportional to 2n minus 1, that is given. So here in this case, W1 is to W2 is to W3 is nothing but H1 is to H2 is to H3. H means like H only, right? It's nothing but H. So 2n means a seconds and the second. So we apply this one. H1, how much? 2 into 1 of 1 is nothing but 1. For H2, 2 into 2 minus 1. So 4 minus 1, 3. H3, 2 into 3 minus 1, which is nothing but 6 minus 1, 5. So the answer would be 1 is to 3 is to 5. Clear? Defining the potential energy in another way. Okay, so work done equal to minus delta U, change in potential energy. Change in potential energy between 2 points is equal to a negative work done by conservative force in displacing the body between those 2 points. You are clear? Let's say you have 2 points. You have 2 points. So between 2 points, if you are trying to displacing the body from one point to another point, right? So the conservative force which is used to display the body from one position to another position is nothing but a work done is equal to change in potential energy between those 2 points is what you say. So the relation between work done and potential energy. So you can represent this like U2 minus U1 is nothing but a delta U, right, equal to negative of FDR integration from R1 to R2, right? So let's look at this way. Du d equal to minus du. So dw means like F into dr, force into displacement. So du means like change in potential energy, U2 minus U1. equal to minus W. You can rewrite this back minus integration of F dr, right? So most of the cases from the potential energy at infinite point we can consider as what? Infinite, right? So at the infinite point the potential energy would be the zero. Normally we consider. So if you look at like you are bringing some the body from the infinite point to the finite point. So what would be the your potential energy, right? You can think of that. So at infinite the work done is zero. If you can put that limits, actually the initial value is like at infinite, but now is a known value r2 which becomes like some r. So minus integration of f dot dr, the limits infinite to r. So this value will become like a zero, and then you will get like a positive value, the limits if you apply. So let's say this is like fr. So final value r minus initial value infinite value, right? So infinite fr at infinite, this is a minus value, right? This would be zero, right? Infinite point is zero. I meant to say infinite point zero, this point is get it, something like this. So that's why we can always think of reference point at infinite would be the zero for the potential energy, and hence the formula can be read as a negative work done. Thanks for watching. Please like, share, subscribe, click on bell icon and leave the comments. Logically, we reached end of the session today. We shall continue remaining in tomorrow's class. Thank you all who are joined and participated actively in today's class. See you all tomorrow. Stay tuned to next session. Thank you. Have a good day. Bye bye.